Check, check. Hello, everybody. Thank you for coming to our next talk, Hacking on the Nanoscale, Dual Beam Devices for Rapid Prototyping and Reverse Engineering. So if you could, please give a round of applause for our speaker, Lorenz.
Thanks a lot, and thanks a lot for showing up here. I'm going to take you on a little journey to the world of dwarfs, or gnomes in English. So I will talk about a new kind of tool that we use in nanoscience, and hopefully we find out, thanks a lot, hopefully we find out how this can be applied to security issues. So what the hell is this talk going to be about? I will do it in a conventional way, so I will first give some background and motivation. I will talk about the basics, so that might be a bit lengthy, but I hope you stay through it. I will show you the actual device, and I will talk about applications like reverse engineering, rapid prototyping, and circuit modification. I will... Closer? Okay. I will give a brief summary, and I have a question in the end that I hope I will get some answers from the audience. So why do I actually give this talk? A great physicist, Richard Feynman, once said, "I believe that we must attack these things in which we do not believe." 2 years ago at the conference in Berlin, the motto was of the keynote, "We lost the war." I actually don't think so. I think we are in an arms race, and although lots of things are playing against us, we might be able to use technology to turn the things a little bit. Briefly to my background, I've been studying physics in Germany, in Regensburg. I've done some research in the States, and since 2005, I'm at the low temperature laboratory in Helsinki, Finland. And as a side job to doing my thesis, I got nominated the FIB expert for this Micronova Center for Micro and Nanofabrication. So that it is called an expert just means that I'm their expert and not necessarily that I am an expert. What I'm definitely not is I'm not a security or computer guy. I know how to turn it on, and I know maybe a bit more, but for the question we have in the end, I need your help. So, what the hell is it all about? It's about nanotechnology. Most of you might have heard about nanotechnology. It's small robots that can swim through your bloodstream and take out these nasty allergens, and they can repair your blood cells, and if things go really bad, they will take over the world and turn everything in a gray goo. At least that's what some people say. It's of course bullshit. So what is nanotechnology actually about? We are dealing with two phenomena. The one is called top-down, which is we have started with microprocessors and other devices. We've started to just shrink the size of the devices to a level that we are actually, since some years now, below the 100 nanometer scale, and we can really claim that we are doing nanotechnology. Another approach that I'm not going to talk about is the bottom-up approach, that people are trying to build machines, devices, something up by self-assembly or by the same means that nature uses. So, but I will focus on material science and electronics. So how does this whole nanoscience work? Of course, whenever you do something like engineering or science, you need a sort of toolbox. The toolbox of nanoscientists are, for one hand, microscopes. This is state-of-the-art scanning electron microscope. We have different sorts of microscopes that were developed in the 80s, scanning probe microscopes, where you actually have a very fine tip with which you can scan a surface and basically achieve atomic resolution. So in addition to that, we need some facilities. In most cases, we have to work in clean rooms because our structures are very small, so even dust particles in the air could seriously destroy our structures. And another thing, especially if you deal with electronics in very small structures, you have problems with heat, and that's why we use elaborate systems for cooling down our experiments. In this case, you see a refrigerator that cools basically down to almost absolute zero. So this is not necessary for all the nanoscale experiments, but whenever you shrink things down, thermal vibration, thermal noise becomes a problem. So the system I'm going to talk about is some chimera consists of a scanning electron microscope and a focused ion beam. If you put these together, you get these shiny devices, and if you buy them with FEI, they are called a dual beam system. If you buy them with size, they are called a cross beam, but the principle is the same. You have two columns that deliver two different ways of imaging. In order to kind of get to what we can do with these systems, I would like to give you a bit of the basic principles of how a scanning electron microscope works. Here, this is pretty new, that was released this year. So whenever you thought that a scanning electron microscope has to be something really big and expensive, these devices actually fit on a tabletop. They are about the size of a very small fridge, and they are just slightly more expensive than a car. So even though you cannot see it here anymore because everything is so neatly integrated, the system is pretty much the same since years. On the top you have an electron gun that in most cases is just a very fine needle. You heat it up and electrons come out. Given that you have this whole thing enclosed in some sort of vacuum, otherwise the electrons would just stop pretty quickly. Like in a light microscope, you have a lens system that transforms and focuses your beam that you get from the gun. The difference between a scanning electron microscope and a light microscope is that you actually create a very tiny beam that is focused on the sample, and then you use these scanning coils to move the beam around on the surface, scan the surface. And while you scan the surface, you collect the electrons that come out of the sample with a small detector in the chamber close to the sample. And if you take the signal, the XY signal from the scanning coils for deflecting here or for the XY position on the screen, you can, if you record the current you get from each point of the sample, you can get a nice image. So how does this image look, and is there a little bit more to the image than is obvious? It depends a bit on how you actually collect the electrons that come out of the sample. So if you look here, you have some incident beam of electrons that hits at some point the sample. It's very small, but unfortunately the electrons are not stopped immediately, but they kind of continue on and cause several different effects. I will not go into detail too much. You have light coming out, you have X-ray radiation, You have electrons, if you have a thin sample, you have electrons that just go through. Some go through without even noticing that there's a specimen, others get deflected. But for the case of the scanning electron microscope, the interesting parts are backscattered electrons and secondary electrons. So backscattered electrons, this is an electron coming from the beam that gets reflected by the material. If you look at those, you get a nice map of the elemental composition of the specimen you're looking at. If you look at the secondary electrons that are created by the incident beam that just kicks out other electrons, then you get an image with more surface information. The focused ion beam is pretty much the same. Instead of electron source, you have a liquid metal. In most cases, it's gallium. You have a small metal tip, and if you heat up the gallium slightly, it forms some small or some thin film, and given that you have extraction voltage, it just sprays off the tip of the needle. So once you have this gallium ions coming out of this tip, you can do the same as you did in the electron microscope. You send them through a lens system. You have again some sort of deflection mechanism that scans your beam over the sample. And the beam, in a similar way like the electrons, creates secondary electrons that come flying out, and you can detect those. So you can use the FIB, the focused ion beam, for imaging. This is pretty straightforward. If you have a very low dose, you get some nice signal. Basically looks like an electron microscope picture. Here we have some metal lines and nothing much different than an electron picture. There's only one effect. If you look at metals that have some granular structure, even though the metal itself is flat, you see all these small islands. This is because the metal lattice is oriented differently in the grains of the metal, and you get some channeling effects. So that kind of reduces your secondary electrons, and this, although the surface is flat, it looks structured in the picture. What else can we do with the FIB? Just watching would be boring, but we can, if we crank up the current a bit and get more of these ions coming out, they are pretty heavy, pretty powerful. So we can actually use them to smash out atoms of the lattice that we send them on. Let's say it's a metal, or in this case we have silicon oxide. And we can do this in a very controlled fashion. So we can actually pinpoint a location and say, here I want to mill a structure, and use the ion beam to remove here the surface material. In this case, someone made a Fresnel lens, and the total diameter of the lens is about 10 micrometer. So those are used for photonic experiments in small lasers, stuff like that. Also, the ion beam can basically mill through any material. We have some limitations. We are basically just shooting heavy particles down, and the material we mill away just flies off the surface. But unfortunately, if we dig very deep, it gets redeposited on the material, so we cannot mill arbitrarily steep canals or structures. There's another thing we can do with the FIB, and that makes it even more interesting than the milling. If we inject with a small needle, if we inject some gas into the chamber, in this more normally you use some sort of carbon compounds that bind to a metal or an insulator. You can deposit the material onto the surface. So this chemical bonds inside this carbon compounds get broken up by the ion beam, and you can locally deposit material. Here you see in the image some substrate. It's some chips on a silicon substrate, and here you see 5 small needles that come in that actually through which the gas that is used for this decomposition is pumped. With that also you can write very small structures. Here we see an example where you have on the one side you have the substrate milled away, and on the upper side there was some insulator deposited onto the substrate by this technique. And if you do it carefully, you can also even create 3-dimensional shapes. So now that we have the basics, what does this device look like? So here we have the newest model from Zeiss. It's pretty small. The electron beam column is here sitting vertical, and under a slight angle on the other side, you unfortunately cannot see it, is the ion column. Here is a close-up of the chamber of the microscope. Here in the middle you see the electron beam coming in. Here from this side, actually from behind, comes the ion beam, and you can mount your sample in a region where the ion beam and the electron beam cross. So that gives you the possibility to use the ion beam to change the surface of the sample while you're watching the whole thing with the electron microscope. Things wouldn't be complete without the hand. So I have this little video that maybe works. So typically you also in these systems have some sort of micro or nano manipulator. Here's some demonstration by Kleindiek. They built these grippers that can pick up nanometer-sized objects. You can transport them within the FIB. You can use the focused ion beam to cut off pieces of interest, take the gripper, move them around, weld them to other surfaces. So this is a pretty powerful tool. So now that we established what we have, what can we use it for? There are several applications. So these devices have become popular within the last, let's say, 5 years. Mainly in semiconductor industry, where they are used for failure analysis. They are most probably also heavily used for reverse engineering. I will show later and explain how that works and why these systems are so great for that. They can be used for rapid prototyping, especially because in a normal process it's very hard to, if you use lithography, it's very time consuming. So you would like to have a process that can quickly create nano-sized structures. And with the FIB you can even create 3D structures. The last thing I will talk about, which I think is the most relevant in this case here on this conference, is circuit modification. So, why is it so nice for failure analysis? So, what we see here is the chip-sided bond of a gold wire, and depending on, so there are many factors governing how this wire bonds, And this is a common cause of device failure, that one of these wires breaks or gets detached from the substrate. So the FIB allows you to basically cut the soft wire and cut through the very hard silicon without changing the surface. So you can here nicely see you get a very clean cut, you get the cut exactly where you want it to be. And you can later on have a very close look on this contact surface between the bond and the chip. Basically, that would be the first stage that allows you to image this whole thing in a scanning electron microscope. If you're interested in more detail, if you want to see structures or structure sizes that are much smaller than, let's say, 10 nanometer, you would possibly like to use a transmission electron microscope. This also has something to do with the first slide, with one of the first slides I showed, where you see that the electron beam, the signal that it generates does not come directly from the surface of the sample, but the electron beam goes into the sample several tens of nanometer. So you actually average over a very large area. So if you're interested in very small structures, you can either reduce the energy of the beam, that unfortunately reduces the resolution, or you can just cut very thin slices. And the focused ion beam does allow you exactly that. So you can, for example, if you have a substrate where you know there's a transistor in the middle, and you have pinpointed that this is the transistor that probably failed, you would like to see why did it fail, what happened. You can use this focused ion beam to cut out a small lamella. Then you would take this lamella with some manipulator, lift it out, put it either in the same device or put it in a different transmission electron microscope, and then you can really see here a slice through the transistor, and you can, if necessary, go down to atomic resolution. Another thing we see here, I will talk about also on the next slide. You can not only, in these microscopes, you can not only look at the image, you can also do, for example, some X-ray analysis, and that very nicely gives you very nice information about the material you're actually looking at. So this is some structure that was done at our university. That's some layers, very thin layers that were deposited in a chemical process. And the question was, how thick are the layers, can we see them, and what do they contain? So you prepare a lamella of the substrate in the same way I described. You put it into a transmission electron microscope or a scanning transmission electron microscope. One just looks through the whole substrate, the other one has also a scanning beam. The difference is not so big when it comes to resolution. Here you can see a picture that almost shows you atomic resolution. Unfortunately, it's a bit too bright in here, but maybe, I don't know. These little dots you see are not exactly the atoms, but this comes directly from the fringe or from the lattice pattern of the silicon. So, as I told in the first slide, when you send electrons into a material, you not only get other electrons out or electrons flying through it, these electrons get decelerated, and decelerated charges create electromagnetic waves. So what happens is you have X-rays coming out of the material. So if you scan your beam very finely over this surface, for example here, there was a line scan taken, so the beam was moved over the surface and some energy dispersive X-ray analysis was done. You get these curves, and what these curves tells you is what material is there. So what it means is you can take any, say electronic, any transistor, a hard drive, take it, make a cut through it, put it in one of these devices, and within a day or so get exactly the composition, how it was built. Probably also, if you know a little bit, the methods that were used to making it. So that's why these devices are heavily sold for reverse engineering purposes. Another nice thing is, since you are able to make very thin slices, you can make the slices and after each slice take a picture and then run this series of pictures to the computer and get some tomography or some 3D reconstruction. So in this case, that was done on a biological sample. For this, it used to be that the samples had to be prepared in a special way, frozen or embedded into some plastic. But actually nowadays, even that is not necessary anymore. You can have a certain pressure in the microscope, so you can, not exactly living cells, but almost living cells, can cut them apart and look how it looks in the inside. So, coming to a more fun part, you can use these devices to create 3D structures. In fact, very small 3D structures. By taking a CAD file, people created, for example, this miniature toilet for this dwarfs, presumably, I don't know. You see the process is not perfect yet, so there's it's not straightforward to go from the CAD model to building one of these structures. But it's something that is worked on and probably will work a lot better in the coming years. This is also quite interesting. There they mounted a piece of graphite on a special holder that could be rotated. So they basically had a mini lathe, and they could mill away. So they had this thing rotating in this direction, and the beam came from the side, and then they could nicely carve out this miniature wine glass. So if you want a very small drink, that's probably the way to go. So now the important part, and unfortunately the one where I couldn't get pictures for. What I could get was this this advertisement I found on a web page that actually a company that offers this service to hardware manufacturers. So they will, if you come with a working or not working chip and say, I would like to have some modifications, but I cannot or I don't want to change the production line, or if I put it in the production line, make this a new process, it will probably take a month or years, and it costs lots of money. So you can go and by hand start editing features on an existing circuit. And since you have all the tools, you can cut through wires, you can drill holes in the surface, you can deposit insulators, you can deposit metals. The only thing you cannot do is make a new transistor, but everything that has to do with wiring, you can do. So what is cast into silicon is no longer unchangeable. So what does it mean in a nutshell? We have this awesome device. We can do lots of interesting things with it. We can create and modify structures on a nanometer scale. We have, if we use it together with the analytical capabilities that are out there, electron diffraction and other things, we can really look at features of interest in a way that was never possible before. There are some limitations. So since you have a very precise instrument, you also have a very small area you're working on. So if the chip is a square millimeter, but you're actually working on a 10 or 100 nanometer scale, you cannot definitely change a whole chip. That would just simply take too long. The other point is that these devices are still fairly expensive, so you need some deep pockets if you want one. Now, the reason why I actually gave this talk. So we are about to buy one of these devices. So we have this really nice tool, and I thought maybe we can do something useful with it. So having this possibility to change, modify circuitry, I thought might actually mean that we can do some things that people did not intend. But this is a problem. I know too little about it. I had the feeling that, for example, where you have hardware that allows you to write in it once, like you would have in an RFID chip, maybe the one in the passport, you can actually change that afterwards and make it rewritable. So if someone has an idea how to do this, or has an interesting idea how to use this tool, I think a lot of people would be very happy to try it out. And thank you for listening.
Does anybody have any questions?
Hi there. Yeah, I was just wondering, because you just said a lot of people would be very interested in trying out any of these ideas. I'm just remembering a few years ago when Bunny gave a talk about hacking the Xbox, when he mentioned to, I think, his university or wherever he was working, that he was using their equipment for analyzing the protocols inside the Xbox. They went completely crazy and said, you can't do this, you're going to get us all in a lot of legal trouble. So I'm wondering, how interested would they really be? Because I think most of the stuff we would come up with would get you in a lot of trouble.
My take on that is, first of all, there's different people making decisions and working with the instruments. So this is a completely different level of hierarchy. So put it like that, I've never seen any of the people making the decision actually in the clean room. So, and I mean, actually, they should be interested in it, because if you can do things, other people might find out. And these instruments, they are few, but they are not like unreachable. You have lots of students. Maybe we are fighting terrorism if we do it.
Any other questions?
I think it would be interesting to use these systems to do smart card reverse engineering, because a lot of smart cards, for example, in Germany it's popular Geldkarte, that use cryptography, and the whole security relies on storing the secret key into the smart card and do not get it out. So it would be interesting to just maybe fiddling out to change the whole chip with soft and hardware to make it expose the secret key that is stored into it. And I'm quite sure they make take some defense tries. My English is very limited, sorry, to just avoid this. But I'm not quite sure how good it works, and I think it would be very interesting to just try it out.
Yeah, that was also my feeling. And I think there are actually no countermeasures. Because first of all, it's a new path of a new attack way. So I think no one has thought about that. And second, there is just no way. What would you do? There's nothing that can stop the ion beam. So I can cut through anything. I mean, it's not as simple as that. Of course, you have to know what you're doing. Basically, you need to know how the chip looks. But of course, if you have two and you can destroy one, there are ways to find out.
Yeah, the Geld card is maybe not a good target because they use per card individual keys. They have the key is diversified, so each Geld card has a different key, so you can't do a lot of nice things with these. But there are a lot of other different systems. For example, the MyFair cards, which we use in our university's cafeteria to pay for the meals, and a lot of people use them for building access control. Their whole security relies on these cards that they use a cryptographic algorithm which nobody knows. It's security by obscurity. They have probably weak cipher with 48 bits, and their whole security lies on that nobody knows the cipher. So maybe you could just open the chip, reverse engineer the cipher, or on these cards actually there's a key stored. You could read out the key if you can make it.
I mean, opening is probably not the problem. Of course, you have some sort of current coming through this whole thing. So I don't know whether you destroy the data, but hey, we can find out.
Well, to the countermeasures, I think I'm quite sure that they try to detect air into the chip, and if air is detected, the whole key is destroyed. So you have to do this in vacuum.
Actually, as I mentioned, this whole thing anyway has to work in vacuum. So.
Sorry?
This is anyway a vacuum system.
Okay. So they detect. They try to detect ion beams because the common attack is to use ion beams to flip bits into registers, and therefore create program failures. And so they try to detect ion beams and just kill the public key as a private key. They try to detect temperature variations that are unnatural and kill the... I think it's quite well secured, but it would be very interesting to find out how well they did that.
With regard to the lack of countermeasures against this type of attack, I know that at least one type of microcontroller conceals its bits for whether or not you can read code out of the chip under aluminum shields. The idea being to prevent those bits being influenced by ultraviolet light if somebody were to depot the chip. Would putting key components of the chip above other ones defeat the ability to analyze the underlying ones using this type of technology?
I'm not sure whether I got the question completely because we have some serious interference going on here, acoustic interference. So you say there's an aluminum cover over the chip?
Over individual fuses on the chip.
I don't necessarily see how that would be a problem.
If the aluminum cover were replaced by, say, other parts of the chip using a three-dimensional construction process, would you... Essentially, I'm saying, is it possible to construct a chip such that analyzing part of it destroys another part?
Yeah, that's probably the case. So this focused ion beam is an inherently destructive method. So whenever you look at something, you change it. That's, to some extent, you can go around that by using in the dual beam systems, using the electron beam to image. But still, if something is underneath the surface, you have to cut it open. But you might be able to repair it afterwards.
Are there no other questions? Okay then.